Hello friends, in today's class we are going to solve question related with TLB mapping and average access time. Welcome here, and we have already seen the mapping, and this is one of the question addressing that mapping part. A CPU generate 32-bit virtual address and page size is 4 kilobyte. The processor has a TLB which can hold 120 page table entry and is 4-way set associative. The minimum size of the TLB tag is so set associative mapping it is using. Set associative mapping it is using. Now, I already told you the division that this is divided into this which part. Again, I'll coming back to you that this is having only two division. One is your tag field and another field that is your set index. Okay. And what part we are going to divide in this case is the P part. What is that P part? Is the page number part. So page number will be divided. Okay, so what is page number here? And here we are given with 32-bit virtual address space, the 32 bits virtual address space, and with 4 kilobyte of the pages, that means 12 bits will be assigned over here and 20 bits will be assigned here. Okay, 12 bit and 20 bit. Okay, because nothing is mentioned about the addressability, we'll assume the byte address. So this size is P bits. Okay, this is the P part and this is the D part. Okay, so we will stick with P, and that is equal to right now 20 bits. Now there are 128 entries are there. The total number of entries in this case is 128 and 4-way set associated. That means it divided into 4 sets. Okay, so number of sets will be what? Number of sets in this case will become what? 128 divided by 4. That will become 2 to the power 7 divided by 2 to the power 2. That will become 2 to the power 5. So now there will be total 32 sets will be there, and for that I need how many bits here? 5 bits will be assigned in this case. How many are left with? 20 total bit, 5 bit assigned over here. The tag field remain with what? 15 bits. So for this question, the size of the tag field will become 15 bits. Okay, so this is the answer for this question. Okay, now we have a question here. A computer system is having 40-bit virtual address space. Okay, so let's just keep on summarizing this question. That will help you always. You remember the data, you not go to the again and again to this question. 40 bits virtual address space, and it is page size is 8 kilobyte. Okay, page size is equal to 8 kilobyte and nothing is mentioned, so I'll just say 2 to the power 13. So out of this 13 bits will become your page offset, and remaining 27, yes, 27 bits will be your page number. So page number is 27 bits and page offset is 13 bits. TLB entries there and organized in 32 sets using having 4 ways. Okay, so 128 entries are there, and this 128 entries is organized into what? 32 sets. Okay, and that means how many bits we required for this? 5 bits we required. Does not maintain any process ID. There may be a 1 entry process ID. The minimum length of the TLB tag is. So what we are going to do, we are going to divide this which part? This P part into 2 parts. One field will be in this case will be tag, and another field will be in this case will be the set index, right? Set index field, and that will be of size 5 bits. So of this 27 bits, we have taken what? 5 bits as the set index, and that will go to the remaining is 22 bits. That will become your tag part, and here the tag will be of size 22 bits. So answer for this question will become 22 bits. Effective access time, I already told you that we have a effective access time How to calculate? So we have equal to TLB search plus we have h time, then I'll write here TLB access, then I'll write main memory access time, okay, and 1 minus h time I will write here what I'll write here level, how level in the page table, level in page table into memory access, okay, main memory access time plus extra time memory access time. Okay, so this part is for accessing the what page table, and this part is actually accessing the main memory for instruction or data. That is the idea. Okay, let's have this question. Consider a paging hardware with TLB. Assume that each page table assume that entire page table and all the pages are in physical memory. It takes 10 milliseconds to search the TLB. Okay, 10 millisecond for TLB search. 80 millisecond to access the physical memory. 80 millisecond to access main memory access, right? TLB hit rate h equal to 0.6. Question is effective memory access time. Okay, effective memory access time. Okay, so effective memory access time will become here TLB search time. What is that? 10 millisecond. That is required for hit or miss. Then what we are having TLB search. I think I haven't done any mistake. TLB search, TLB access. So that is the search time. Okay, so TLB search time. Access time is not given. We'll skip it. Memory access time is given. Okay, the H time. Sorry. We have H time. H time, H into what? TLB, H into here, what we have is TLB access time, not given, memory access time, H time. Okay, H is here. Sorry guys. Okay, 0.6 into memory access time is given here, in this case is 80. So I'll put 80 over here. And 1 minus H. What I have to see that assume that entire page table, so nothing is mentioned about the level, so one level page table. So here 80 for page table and 80 for main memory. Okay, let's calculate this. 0.6, this will become what? 48. This will become 0.4 into 160, right? 80 and 80, 60, and 60 into 4 is 24. Right, 40% of, okay, let me write 160, and that will become 10 millisecond plus 48 millisecond plus what will be this 64, right? So that is 1112, and that is 10, and that will become 122 millisecond. Okay, so this is one question. Had this been levels here, in that case we are going to add more number of memory access time here in this case. Okay, so that's all for this discussion. I hope this small discussion of this page tables will really help you in this case. Okay, so that's all for here. Thank you.